So this year's objective was to provide an opportunity for university students, postdocs, and faculty members with a chance to conduct hands-on experiments with Category 1 special nuclear material at the DAF. We worked with Los Alamos to plan and execute these experiments out of the device assembly facility this summer, and the experiments took place the week of July 6th to the 9th. And these were some of the first ever university-led experiments at Cat 1 at S&M at the DAF. So that was pretty cool. So a little bit about the DAF. It's located about 90 minutes northwest of Las Vegas. And it's operated by National Securities Technologies. So you can see the building, it's partially underground. The DAF is set up to support critical and subcritical measurements of weapons-grade plutonium, highly enriched uranium, and neptunium. So here we have the list that I think we saw during lunch of the fissionable sources. So you can see the weapons-grade plutonium, they have both metal and oxides. For the highly enriched uranium, they also have both metal and oxide, and apparently a hydride, as well as they have neptunium. In addition to the fissionable material, they have a wide range of reflectors and shields that you can use, covering the low, mid, and high Z materials. So this year's participants included North Carolina State and the University of Michigan, and they were assisted by Oak Ridge National Laboratory's Jason Newby and Los Alamos National Laboratory's Jessen Hutchinson. So the experiments that we chose to run this year involved the Burt Ball, which is a 4.5 kilogram sphere of weapons-grade plutonium metal, the Iraqi flat shells, which we used a total of 13 kilograms of highly enriched uranium metal, and the Thor core, which we only used one piece of it, and we'll go into that in a second. The piece we used was about 4 kilograms of weapons-grade plutonium in a disc format. So we imaged all of these sources with bare or no shielding, and then we also imaged them with polyethylene, iron, and tungsten to cover the range from low, mid, and high Z materials. Lastly, the instruments we used, North Carolina State was using the fast neutron-coated aperture imager developed by Oak Ridge and Sandia National Laboratories. We have the dual particle scatter imager, which was developed by the University of Michigan, as well as the Polaris and Orion Compton scatter gamma imagers developed by the University of Michigan. So here we have the Burt Ball. This is the 4.5 kilogram sphere of weapons-grade plutonium. It's in its alpha phase, and to give you an idea, it's about the size of a baseball. The alpha phase of plutonium is a higher density than the normally seen, or the other normally seen phase of plutonium metal, which is the delta phase. And it's got about 19.8 or 19.9 grams per cubic centimeter compared to 16 grams per cubic centimeter. It's clad in a stainless steel shell. We have the Iraqi flat shells, which seen here are shells 3 through 24. There are a lot more than that. There's up to about 50 kilograms of total shells, but they restrict the use to these shells. While they're in use, they're encased in an aluminum sphere to prevent contamination from getting out. And due to the low spontaneous fission rate, these experiments were driven either by a californium-252 or an americium beryllium source. So here we have the Thor core, which is technically 4 pieces of delta phase plutonium. We chose to image the center piece, the center disc, which you can see with the dotted line, actually has a pin cut out of the center of it. And then, so the other 2 pieces are the partial hemispheres. We chose this one for its interesting geometric configurations that we could image and then discriminate against. So North Carolina State, like I said, uses the coated aperture imager, which is a 4x4 array of EJ299 plastic scintillators, which are PSD capable. Each EJ299 detector is then split up and optically segmented into a 10x10 array, giving us a total of 1,600 pixels. Recently, they've added a thin film of lithium impregnated zinc glass, which, with the N-alpha reaction on the lithium, we are then sensitive to thermal neutrons as well as fast neutrons in gamma rays. So the mask in front of the detectors is what's known as a uniformly redundant array, and therefore if it's rotated by 90 degrees, it becomes its own inverse or its own anti-mask. And we need to be, the distance is important because that sets the field of view and the focus, so we try to be about the same distance from the source to the mask, and the mass to the detectors. So for our analysis, we need to exploit the dynamics of fission chains. So I think we saw this earlier in Dr. Mattingly's talk, but one more time couldn't hurt. So let's think about it on a time frame, and this time frame is on the order of shakes. So imagine we could see an individual fission, and then we got a count from that fission. And if we see that the energy of the proton, the recoil of the proton is less than that of the apparent neutron, that's what we would expect. However, if we have the same scenario and we see the energy of the proton is greater than that of the apparent neutron, one possible explanation is that it came from a fission chain event. So the way we determine the time is we take the preceding gamma rays time and correct it for the detector distance, and therefore the neutron time subtracts off that preceding gamma rays time to get our time of flight. So with this information, we can dissect the energy and time phase space into two. The region below the curve is where the energy of the proton is less than that of the neutron, and the region above is obviously where the proton energy is greater than the neutron energy. Below the curve, we would not have any fission chain events, and they would just be first generation. So above the curve is the possible fission chain events that we're looking for. So we went ahead and used our coded Aperture image here to do some reconstruction, and here we have the overnight run of the burp ball on the Californium source, and you can see with the top right image, we can clearly distinguish the two sources, and each tick mark here, they're represented in centimeters, so these are about half a meter apart. So if we make certain energy cuts on the gamma range, we can isolate just the plutonium in the gamma image. So if we make a cut between 30 and 650 keV, which is the region of interest for plutonium-239, we can effectively get rid of the Californium in this picture. So doing our image analysis on this picture, you can see the top left is another setup where the two sources are about 30 to 40 centimeters apart, and it's conceivable that we could even discriminate these two sources at an even closer distance. So when we do an image reconstruction on this, only looking at fission chain events, we can take an X projection at the location of the burp ball, and we can see that in the top right histogram, there seems to be a source present at the location of about a couple centimeters to the right of 0. Whereas if we take an X projection at the location of the Californium in the picture, it just fluctuates back and forth. And so there's no evidence of there being a source there in the reconstructed fission chain event image. So in addition to the burp ball, we've looked at some of the information from the Thor core. Well, what's really cool here is we can show off the spatial resolution of the coded aperture imager. You can see that we've imaged it in all three configurations, and we can tell how the Thor core is facing. So you can see the circular flat face, if it's horizontal, or if it's vertical. Again, here the tick marks are in centimeters. So lastly, we looked at the Thor core encased in polyethylene, and so you can see the fast neutron image on top. We can still tell what the orientation of the Thor core piece was, and on the bottom you can see a halo of thermal neutrons that represents about 25 centimeters in diameter, which is the diameter of the polyethylene sphere that's encasing the Thor core. So with that, I'm going to hand it over to Mike. He's going to tell you about the dual particle imager.
Thanks, Jack. So I'm going to speak about the dual particle imager. We had several goals and objectives for this campaign. I think the first one was, it should be fairly obvious by now that this is not like measuring californium in your lab. So we really wanted to compare or figure out how our system would perform in the presence of actual Category 1 special nuclear material. Along with that, we wanted to acquire some benchmark data, do some really long measurements, get some good spectra and images for this special nuclear material. And then we wanted to look and see if our system could distinguish special nuclear material in the presence of other neutron and gamma ray sources. So just a quick overview on the dual particle imager. It's a two-plane scatter camera. It's a combination of a Compton scatter and a neutron scatter camera. It uses EJ309 liquid scintillators and sodium iodide scintillators. And we've designed some custom algorithms to go through and process this data. It relies on pulse shape discrimination in the liquid scintillators. We have some custom data acquisition and online processing software, as well as event correlation scripts. And then we're working now to develop some advanced imaging and spectroscopy techniques to further analyze the data. So just a quick overview of the physics behind the system. For a neutron event, we're looking for a single scatter in one of the front plane liquid scintillators, followed up by a subsequent scatter in one of the back plane liquid scintillators. And then using the time of flight, we're able to reconstruct a cone of the possible origin from that event. Similarly, for photons, we're also looking for a single scatter in one of the front plane liquid scintillators. But now, instead of looking for another scatter in a liquid scintillator, we want a full energy absorption in one of our backplane sodium iodide detectors. This will also give us a cone of possible source locations. And then once we superimpose these cones, this is going to create a back projection image and help to localize our sources. So, this table didn't show up. Shoot. All right. Well, one of the challenges we faced was that the low energy photons can really overload the data acquisition system. It's going to produce a lot of light in the detectors. And the photon that we were most worried about was the 59.5 keV line from americium-241. In units of, I believe it's gammas per gram per second, it's about 10 to the 10th. And then there's some other counts from the plutonium-239. We really wanted to see those. Those are in the like the 450 keV to about 600 to 700 keV region. So to mitigate this problem, we needed to kind of combine using a lead shield. We ended up using about a 1/2 inch. You can see it in this picture down here, as well as using a higher threshold in the sodium iodide detectors. So we kind of put that in the range between the 59.5 keV line in this other region of plutonium-239 gammas that we wanted to preserve. So these are a couple of results. The top image is a neutron back projection image. This is just from the burp ball. So it's a point source, and as you would expect, you see a single hotspot. And then the lower image is a separate photon image. So what's great about our imaging system is we can get both a separate neutron and photon image, which is great if there's any sort of intervening material in between to have both those signals. We also reconstruct the energy spectrum for both the neutrons and the photons. You can see those on the right of the slide. The top plot shows the neutron spectra. And it was also really cool, we had some different moderators that we were able to put around these sources. So this provided us a very good comparison and really showed us what you could expect in terms of neutron counts and photon counts. And we'll be able to go through this and kind of analyze, what was the multiplication of the source with that moderator and how would we expect that to change the count rate. So for future treaty verification purposes, this is really going to help us to design the system. So the coolest measurement that I think we did, we used the Thor core, Californium-252, and an ambi source simultaneously. And this slide, it shows the photon results from that measurement. This is using MLEM reconstruction now. My colleague Kyle Pollack's done some really good work to be able to deconvolve the photon spectrum and actually isolate it from each of the hotspots. So if you look, you can see there's a hotspot for the Thor core as well as the Californium-252. And then if you come down to this plot, you can see that the blue curve, which is the photon spectrum from the Thor core, you kind of see two distinct peaks. And that's going to be these two regions that you would expect. The lower region is going to be counts from the plutonium-239, and that upper region is going to be some counts from plutonium-239 and also americium-241. You notice you don't see the ambi source. We had this pretty heavily shielded with lead. You can see it in the picture. There's probably 4 or 5 inches of lead. So we don't see a photon image. And again, this is where having the dual particle imager comes in so handy, because if we look at the neutron image, we now see that ambi source really shows up with a very distinct hotspot. So again, if you deconvolve the neutron spectra, you can see that, as we would expect, the ambi source is going to have a lot of neutrons at higher energies than the Thor core and the Californium-252, which is going to be the watt spectrum, as you would expect. So we were able to produce images from Category 1 special nuclear material, mitigate the high gamma ray flux, especially from that low energy americium, and we were able to discriminate multiple sources and show and identify S&M in the presence of other neutron and gamma ray emitting sources. If you're interested, you can read more about the DPI. These slides are on the website. And I'm going to hand it over to David.
So I'm a member of the Orion Radiation Measurement Group, and as a group we focus on room temperature imaging spectrometers. And within this focus we have several research areas of interest, one of them being reconstruction algorithm development. We work on Compton imaging, coded aperture, and time-encoded imaging, as Professor He mentioned earlier today. We also work on material imperfections and diagnosing them in semiconductor materials, primarily CZT and thallium bromide. We also work on digital readout and digital post-processing using our systems, so we can better leverage them in practical applications and how we can use these in the real world, such as nuclear power, treaty verifications, and safeguards. And we'll be focusing on the results from this practical measure that we had the look to take at DAF. So we took two systems to DAF. The first system is the Polaris Separable Plane System, and we call it the Polaris SP system for short. And this system consists of 2 centimeter by 2 centimeter by 1.5 centimeter CZT crystals shown here on the left. And these crystals are gridded up in arrays that are 3 by 3. So you have 9 crystals per array. And you have 2 of these 9 crystal arrays for our total system, for a total volume of 18 crystals. And I'll mention that this system relies on analog pulse readout. And for the rest of this presentation, I'll be focusing on our other system we brought to DAF, which is our Orion system, which relies on digital pulse processing. And notably, this Orion system is a little smaller. It consists of a 2 by 2 array of CZT crystals, but we can use our ASICs, or our application-specific integrated circuits, to read out the triggered waveforms from our pixelated anodes. And by reading out the triggered and neighboring anode pixels, we can get sub-pixel resolution using our system. And this will be very important for the subsequent slides I bring up. So shown here on the right is a flood image of one detector recorded using a cesium source. And you can see that we can deduce interaction locations to smaller than the size of 1 pixel pitch on our detector. And notably, using these high-quality crystals and pulse readout technology, we can get pretty good energy resolution. And this detector shown here is reporting about 0.4% full width half max. And notably, this is for one single detector, however. So now on to what we learned from this measurement. Shown here on the top left is our measurement setup, where we had the HEU shells that were mentioned previously with an ambi driver right next to them. And we imaged this geometry using our Orion system and a 3 millimeter thick, 2 millimeter diameter pinhole. Shown here in the bottom left, and I guess my color scale did not show up, compares the relative contributions of the 60 keV line from the ambi driver and the 186 keV line from the HEU spheres. And you can see from the shadow cast through our pinhole on one detector, there's a region of the shadow that is dominated by 60 keV, shown in the red, and a region dominated by 186 keV, shown in the blue. And when you separate these images on the same detector by bending on photo peaks, you can see very clearly a separation between the shadows cast from the americium source and the HEU source. And notably, the HEU source appears larger in size and appears extended compared to the point ambi driver. As mentioned previously, we didn't only measure HEU at DAF, we measured the Thor core, and this is the central slice of the hockey puck Thor core that Jack mentioned. So it's 4 inches in diameter and about 1.5 inches thick. We rotated this Thor core through several geometries and imaged each geometry using our pinhole system I mentioned previously. Shown on the bottom left, if you imagine the hockey puck is facing you, right on you, you are seeing a projection that is a circle, or contrastingly, for these subsequent measurements, you're viewing the hockey puck from the side on, so it appears as a line in different directions. And from the shadow we record using our pinhole camera, there are different apparent relative geometries. So we can successfully determine, using our system, what the relative source geometry was. And an unintended benefit of measuring this Thor core is we took a very long measurement overnight using our Orion system where we only considered single pixel events, which we have our best energy resolution on. And you can determine the Pu-240 content in an object by looking at this complicated region of the spectrum shown here highlighted in pink. Notably, this is a very busy part of the spectrum, as you might expect, and the Panda manual references many, many lines where only one of them, which is not very prominent, is from Pu-240. But using some advanced spectral processing techniques, such as those provided by Scott Gardner from Hamel, we were able to determine the plutonium-240 enrichment in the central slice of the Thor core as 3.63%, while the actual value is 5.02%. So when you look at the quoted uncertainties of these values, we are reporting 3.63 plus or minus 1.02. The true value is within 2 sigma measurement uncertainty of our reported measured value taken at room temperature, which is exciting. So the line we are looking for from plutonium-240 is this line here highlighted in red. And as Professor He mentioned earlier, although you can't really see a well-resolved photopeak, you can tell by peak fitting the relative contribution of this line and every other line around it to get a photopeak area that you can therefore deduce Pu-240 content from. So I will just briefly discuss our successes and I'll hand it off to questions. So we successfully imaged through a HEU extended source using both our pinhole camera and using our analog system. We also took coded aperture measurements that were successful. We also could image relative Thor core geometries and in this process determine its unknown plutonium-240 content to within 2 sigma at room temperature. So I'll thank everyone. I should also mention there'll be a subsequent measurement campaign in 2016. If you're interested in participating, you should contact either Professor Posey or Professor Mattingly. And we'd like to thank everyone who had this, allowed us to take these amazing measurements in an amazing facility. So we'd like to send our sincere gratitude to both Justin Hutchinson and Karen Miller for helping this be possible.
This South African station here has been moved to the mainland of South Africa in the meantime, since 2010 and now. So just saying we are